Okay, so we're picking up from what we did last Thursday, and last Thursday we went over these three different types of nuclear reactions. We covered alpha emission, beta emission, and positron emission, and we talked about how this could also be referred to as alpha decay or beta decay, that something will decay by alpha emission, and then that produces radiation, right? So then you've got alpha radiation that came from the alpha emission from an alpha decay, and so on and so forth with the beta emission. And then gamma radiation is formed when you have positron emission. And we talked about that penetrating power. All right, so today, what we are going to do is cover these three: electron capture, nuclear fission, and nuclear fusion. And when we finish with those, we're going to talk about half-lives and like carbon dating kind of thing. All right, so we're going to start though with these three types of nuclear reactions. And again, we're going to use all these same symbols that we're familiar with, and the elemental symbols that we're familiar with. And the same rules apply that we learned for alpha, beta, and positron. That is, your total mass is going to add up on both sides to be equal. And your total number of positive charges is going to add up on both sides to be equal. All right, but electron capture. All right, so electron capture occurs, and I'm just going to copy this over from my lecture notes actually. If you could see that. Okay, so this is electron capture. And as I note here, it's kind of the opposite of beta emission. So in beta emission, your nucleus is going to kick out an electron. And we said, that's weird. Where did your nucleus get an electron? And we decided that your neutron would decay into a proton and an electron. Let's see, here's our beta emission. So your neutron decays into basically a proton and an electron gets kicked out. And then your nucleus gets converted here. All right, so in electron capture, the nucleus is going to capture one of your innermost electrons and say, I want you. And so you're going to have an electron here, but it's going to be on the left-hand side of the equation, in the reactants side of it, okay? So what it's going to look like, hang on. Okay, so here, mercury 197 decays by electron capture, and it forms gold 197. So again, we can see we have 197 plus 0 is equal to 197 on the left-hand side, on the right-hand side and left-hand side. And then we have 80, and then we could say plus a -1 is equal to 79, right? And essentially what's happening here is, as the electron gets absorbed by the nucleus, that negatively charged electron is going to be attracted to and fused with a positively charged proton, right? And so what you're essentially getting is the 1,1 proton combining with the 0, -1 electron. And you can see what's going to happen with that. Your mass of 1 plus your mass of 0 gives you a total mass of 1, and your charge of +1 plus your charge of -1 gives you a total charge of 0, and your particle with a mass of 1 but no charge, that's your neutron, right? So that's what's happening inside the nucleus while we have this mercury converting into gold here. So this is actually a way to transmute mercury into gold, but it's much more expensive than it would be just to find gold out in the world. And so even though this looks like transmutation, it's not really commercially feasible way to make gold if you wanted to make gold, for instance. All right, let's give you guys one. Arsenic 77 also decays by electron capture. Can you tell me what other species would be formed? Good, so we're gonna have 73 plus 0 equals 73 on top, and 33 minus 1 equals 32 on the bottom. And then you just look at your periodic table for element number 32, and that's germanium, and there's your answer. Erica has a great question. She says, this is the symbol for beta emission. So would I ask us this and expect you to say electron capture? The answer is yes. Now it's the symbol for beta emission, but it is an electron, right? And just to compare, I'm going to put these right next to one another so you can see how they do look different, okay? In beta emission, that beta particle is being emitted. It's being kicked out. And that's why if you're nearby, you would be exposed to beta radiation. And electron capture, that electron or beta particle is being captured by the nucleus. So it's being added to the nucleus instead of being kicked out from the nucleus. And so the nucleus changes, but you don't see anything in terms of emission or radiation that you could measure to say, hey, there was nuclear chemistry going on. It's kind of silent, right? So arsenic might be sitting here and slowly converting without actually causing any problems or emitting any radiation whatsoever. And unless you're measuring the amount of arsenic and germanium present over time, you might not even know that there was something happening. Do you see the difference here between the two? Just to clarify, this is beta emission. And of course, this one is my electron capture. Okay. All right, so that's electron capture. So you have the beta particle, but it's on a different side. So pay attention to the word. So a capture means that that nucleus is capturing it, and the emission means that the nucleus is emitting it, and that'll kind of help you follow it to see what direction it should be going. Okay, good. Next we have nuclear fission. And your nuclear fission occurs when a nucleus falls apart, literally. So in the process, you might get any number of nuclear species. It might just fall into 2 pieces. It might fall into 3 or 4 pieces. This often happens with very large nucleuses. They just start to become unstable over their own size. And so they might just fall apart all by their own. Now, that's not always the case. It might also be true that you can help induce it to fall apart by like bombarding it with something, right? So let me copy and paste these here. Here we go. Nuclear fission occurs when that nucleus falls apart, literally, okay? So again, you might get more than one thing, but the important thing is that it falls apart, and you're going to look at the overall mass to kind of see how this happened. So here's an example. Uranium-235 is a unstable nucleus, maybe semi-stable nucleus, but it's really big. If I just hit it with a single neutron, it's like shooting it with a bullet, right? And the whole thing just falls to pieces. It just can't hold itself together. And so this is fission, because what I see on the left-hand side is a mass of 235. And on the right-hand side, I see multiple masses, but none of them is close to 235, right? So clearly this was a big thing that fell apart into multiple little things, okay? Hopefully you can see that. So that is fission. And fission is the is what all of our nuclear reactors providing nuclear energy run on, is fission reactions, right? And so what happens is that you are going to form some of these other things, It fell apart happily, but there's not necessarily a guarantee that these products are particularly stable either. And so some of them might continue to fall apart and produce alpha or beta or gamma radiation. And that's why, for instance, there ends up being nuclear waste that has to be stored essentially from these. But hopefully you can see, again, we're following all the same rules, although it takes a little bit more doing to add it up. We have a total mass of 235 plus 1, so that's 236 in my reactant side. And then on my product side, I have a total mass of, let's see, we've got 91 plus, we've got a 142 plus, and now I've got 3 neutrons. So don't forget, if you have a coefficient here, that you have to multiply whatever mass by that number. So 91 plus 142 plus 3. If I plug that into my trusty calculator, I get a total mass, as you can see, of 236. And on the bottom here, we have 92 plus 0 positive charges, so that adds up to 92. And that should, if this is done right, that should equal 36 plus 56 plus, now we have 3 times 0. Now it's going to be 0, right? So we can see 36 plus 56 does in fact equal 92. They equal 92 on both sides. So this still meets our criteria for being a reaction where mass and charge is conserved overall. Does that make sense? Okay. Now, this is actually, and I need to call you out on this so you can recognize this, because you've got a sample of uranium-235 and you're hitting it with a neutron to make this go, and it makes 3 more neutrons. What's going to happen next? Well, if I've got, good guess, Erica. Yeah, if I've got uranium around and I know that hitting it with a neutron makes it fall apart, and during the process I make more neutrons, then those neutrons are going to go off and bombard other neighboring uranium-235 atoms and start more nuclear reactions. And so this is the beginning of what you would call a nuclear chain reaction, because, again, at the beginning, you just need 1 neutron to break it apart, and that makes 3 more neutrons, which can then break 3 more nucleuses apart. And if each of those does 3 more neutrons, then what? If you have not been careful to control this reaction, then you're going to have a meltdown on your hands, and it's not going to be pretty, okay? It's going to run away from you. And this is one of the reasons, for instance, that nuclear reactions and nuclear energy can be dangerous. Right now, we're on to, several generations later of nuclear reactors. They're very safe, but there's always this specter of danger, right? That another Chernobyl or another 3 Mile Island could happen, and another Fukushima reactor, for instance, could happen, and that could cause some serious problems. Anyways, so that's the chain reaction. All right, so let me give you another one here. Maybe you can tell me what else forms. Now, sometimes, especially for these very large nucleuses, this is not something you can easily predict, right? I could shoot a neutron at uranium-235. Depending on where it hits, I might split it this way, or I might split it a different way, right? It's not going to do what you tell it. It's not like a chemical reaction where it has to meet these rules for where the electrons go and how they get shared. Instead, it's just going to be like, I'm going to fall apart into something that feels more comfortable, and there's multiple ways to do that. So even though both of these start with uranium-235, shut up with a neutron, then they don't necessarily produce the same products. So help me figure out what else am I gonna make here? All right, Sarah says, look, I've got 235 plus 1, so I've got 236 on the left-hand side. And that's got to be equal to whatever I've got here. And whatever I've got here is x plus 137 plus 2 times 1. And so if I solve for x, I'm going to take 236, subtract 137, subtract 2, and I get a total mass of 97 on the top. All right, not so bad. And then Sarah did the same thing down here. She says 92 plus 0 is 92, and that's got to be equal to, we'll call this y, plus 52 plus 2 times 0. Okay, so we pull out our calculator and we said 92 minus 52 gives me y must be 40, so 40 on the bottom. And then she looked up element number 40 on the periodic table and said, all right, that's got to be zirconium. That's the other thing that was formed there. Any questions on fission? Okay. All right, well, let's talk about the next thing we want to talk about, which is the fusion reaction. So in nuclear fusion, it's like the opposite to nuclear fission. Let me write this down. Okay, so nuclear fusion occurs when 2 or more nuclei fuse together to form a single larger atom. Okay, now like fission, this releases a lot of energy, right? So most of our nuclear reactors, all of our nuclear reactors, are working on fission. We would love to find a fusion reactor. That technology hasn't matured yet, if it ever will. It's kind of the holy grail of energy. But cold fusion, as they call it, would revolutionize our world in terms of energy usage, because you can get a lot of energy from it just like you can from fission, but it doesn't create nearly the amount of radioactive side products. And in fact, it's a much safer, hypothetically, and a much cleaner form of energy. All right, this is actually what the sun does, right? So your sun starts with hydrogen and it fuses it to form helium over time, and it releases so much energy that you get, life on Earth essentially. That's just soaking up a tiny bit of that energy. And when it starts running out of hydrogen, then the helium will begin to fuse and so on and so forth, all the way up to iron. But those are all favorable reactions that will release energy. Well, let me give you an idea here what this looks like on Earth. Scientists will fuse things together. Usually they'll bombard, or maybe they'll shoot, say, this silver atom with a helium atom, and then they'll collect the molybdenum that's formed, right? So again, just to confirm, we have a mass of 109 plus 4 on the left-hand side, and that is equal to our total mass of 113 on our right-hand side. And in terms of our positive charges, 47 plus 2, and this is going to equal 49. Okay, now this looks a little bit like, that's an alpha particle because it's helium, but this is not alpha emission because, again, this helium is not being emitted as a product, it's being absorbed, right? And these two things are fusing together to make something else. Am I wrong about 49? Sarah's a good catcher. Okay. Sarah says, element 49 is not molybdenum, it's indium. Thank you for catching that. That's an error on my lecture notes. You guys are good. I'm impressed. Let's fix that right here. There we go. All right, so pardon me. This is what we get. Silver bombarded with helium forms indium. Now this is actually how something like a new element gets quote unquote discovered, right? Is they do these kind of bombardment reactions. And it's not, you know, when you hear about, oh, such and such new element was discovered, you think somebody maybe just like found it by the side of the road and was like, this is interesting, right? Like this still happens with biology all the time, right? There's some field biologist who's out hiking and notices a flower that seems out of place and takes a cutting and brings it home and runs a genetic analysis and was like, this really is a different thing. And that happens all the time, but that does not happen anymore with chemistry. We've found all the naturally occurring ones, and now at this point we're just synthesizing ones based on hypothetical masses and number of protons to try to see if we can get one that's semi sort of stable, which none of them are at this point. But that's a different story. But yeah, this is what nuclear fusion looks like. And again, I'm going to draw your attention to this. This is how you're going to tell the difference between fission and fusion, is that the highest mass piece is on the right-hand side instead of the left-hand side, right? So this looks like two smaller things got together and made something bigger. That's fusion. Do you guys see that? Okay. All right, let's give you another one. Here's your next example. Californium-246 was formed or could be formed by the fusion of uranium with one other species. Now here's the thing with discovering an element, you get to name it, right? And then it's enshrined for all eternity. And so it's exciting to have a program to quote unquote discover elements, because then you get to name them, put them on the periodic table. So californium and berkelium and americium, all of those are reflective of the fact that for a long time we had an excellent nuclear chemistry program at UC Berkeley in California. Okay, and that's where those come from. All right, Sarah has got this. She says on the right hand side now, 246 plus I've got 4 times 1. That gives a total of 250 on the right hand side. So 238 plus what is equal to 50? She says the answer is 12, right? That's going to get me there. Hang on, I'm a little bit. Bring this over here. See it more clearly. Oops. Okay. And then on the bottom here, 92 plus what is going to give me, we've got 98 plus 4 times 0. So 92 plus what gives me 98? The answer, of course, is 6. So, and I, okay. So this becomes 12, 6. Carbon is the thing that uranium was fused with to make californium in this instance. Now, don't be fazed by the fact that there's other stuff going on. You know, there's parts left over. This might fuse together, but some other stuff might just be kind of shot out to make sure that it's stable. So it might just kind of decay that way. And so Sarah says, would you give us a problem like this, but you find the 410N instead? I could, but I would have to give you the 4, right? Otherwise, you would end up with a species of like 40, and you're like, that's not a thing, right? So I would either say 410N, or I would say how many neutrons. You could solve for that. But there's, you know, I can only give you one variable here. All right. So this one looks a little bit confusing. if I said, is this fission or fusion? Again, just to remind you, look for the highest, the biggest thing. So we've got 238 on the left and 246 on the right. This is the biggest thing, the largest mass. So we had combined two smaller things to make something even bigger, even though this was already big to start with. This is even bigger, so that is a fusion reaction. And then just gonna put this in here. This is what happens in the sun. It's a deuterated helium, so that, or hydrogen. So hydrogen with a neutron and a proton. These combine to form helium, and then gamma radiation or energy is formed as an aside here. Any questions about fusion, fission, or electron capture? Okay, well then I'm just gonna copy this from your worksheet. We're gonna do some practice problems, okay? Now again, some of these are fission, and some of these are fusion, and some of these are electron capture. And we need to identify them and then solve for the missing piece, okay? So let's start with identifying, actually, you know, for some of these, it might help to find the missing piece first. Let's find the missing piece. That will make our lives easier. So for this first one, we've got boron 10 and helium 4 combining, and we do end up with a neutron left over at the end of the day. So 10 plus 4 is 14 equals 1 plus 13 on the top. And then 5 plus 2 is 7, and that's going to equal 0 plus 7. So this is going to be a 13, 7. Can you guys still see that if I make it a little bit smaller? And then being a 7 makes it a nitrogen. Is that too small? Can you guys see that? Okay, good. All right, how would you guys characterize this then? Fission, fusion, or electron capture? This is fusion. Good job, Erica. It's fusion because the highest mass item is the one on the product side. So we made something bigger. We fused these pieces together. Good. All right, let's see. We've got bismuth 209 plus iron 58 goes to form something plus meitnerium 266. And I'm gonna need a calculator for this guy. 209 plus 58. So 267 on the left-hand side is gonna equal 1 plus 266 on the right-hand side. Okay. All right, and then 83 plus 26 on the left-hand side equals 109, which is what I already have on the right-hand side. So that's gonna be a 0. And a species with a mass of 1 and a charge of 0, that is a neutron. Is this fission, fusion, or electron capture? Yeah, fusion. This is a little bit easier to see. Well, I don't know. 209, 58 versus 266 in the product. Okay, here we go. Boron 10 again. Hit it with a neutron and I get 42He plus, okay, so 10 plus 1 is 11. That's going to equal 4 plus 7 on the top. And then 5 plus 0 equals 2 plus 3 on the bottom. And element number 3 is lithium. Good. And this is fission, as you guys have noted. Good. Because your highest mass piece is on the left, it's this boron. Now, this would not be categorized or characterized as alpha radiation, not necessarily, okay? Because this wasn't a spontaneous decay of the boron that led to alpha emission and alpha radiation, but rather this was promoted decay, right? You hit it with a neutron and then it fell apart. And so while you might get what would look like alpha radiation, it didn't come from a naturally occurring alpha emission event. Does that make sense? All right, let's look at this guy here. 238 plus what equals 246. Is this the example that we just did over here? Let's see. Yeah, this is right here. This looked really familiar to me. 238 plus 12, 6 carbon, gives me californium 246 plus 4, 1 nitrogen. Sarah, did you calculate that all over? Or did you recognize that we had done that one just now? Good, it's not hard to do it again, just curious. All right, so 238 plus 12 gives me 250. 246 plus 4 times 1 gives me 250. And then 92 plus 6 gives me 98, which is 98 plus 0. Okay, and is that, you said fusion, yeah. Because the californium is the highest mass piece there in the product. Okay, here we go. And I just showed you this as an example. 2 plus 2 equals 0 plus 4, and 1 plus 1 equals 0 plus 2. I would never have you guess at gamma radiation being formed because it has no mass and no charge here. But if I showed you that it was there and then you said what else was formed, element number 2 is helium. So this is stars, how stars are born, right? The hydrogen collects in what you would call a stellar nursery, and once it reaches a certain mass that there's enough pressure on it, then it starts to undergo that fusion reaction. Okay, nickel 59. We have 59 plus 0 is going to equal 59 on the top. 28 plus a negative 1 gives me a 27 on the bottom. Element number 27 is cobalt, and hopefully you see here that's electron capture because I am adding that electron to the nickel. Yes, oh, you guys did tell me this is fusion. Here we go, we've got uranium 238, and we're gonna shoot it with a neutron, and we're gonna get something else plus a couple of electrons. Okay, so 238 plus 1 is 239, and 239 equals 239 plus 0. Okay, because this is 2 times 0. And then 92 plus 0 equals, this has got to be 94 because I'm going to end up subtracting 2. So 2 times a negative 1 is negative 2. So 94 minus 2 gives me my 92. And then the 94 on the bottom means I'm going to be element plutonium here. Okay. And then Sarah says this is fusion. Exactly right. This one is hard because you're like, well, is it making something bigger? Well, yeah, actually, it's a tiny bit bigger. It doesn't have to be like way bigger, right? If it's a little bit bigger, then you still got that neutron to fuse to the uranium. And you might say, yeah, well, I added 1 neutron, but I lost 2 electrons. Yeah, no biggie. Electrons have basically no mass. Not actually no mass, remember, but relative to everything else, they're just so tiny we don't care. We did get that neutron to stick, and now we've got plutonium. Do the numbers not match? Did I miss something here? We should have, on this side, we have 92 plus 0 is equal to 94 plus, and this is going to be a 2 times a negative 1. And on the top here, we've got 238 plus 1 is equal to, this is going to be 239 plus 2 times 0. I think that matches. Okay. It's always good to double check. Will never hurt you to double check. You've got time, so you should use it. All right. Last guy here, we've got aluminum 2613. So 26 plus 0 gives me 26 on the top, and then 13 minus 1 gives me 12 on the bottom. And element number 12, if you're checking the periodic table, is always a very good idea. Should be magnesium. And this is going to be, as Sarah noted here, it's electron capture. Yeah, and Erica both, yes, because you are capturing this electron, right, and absorbing it into yourself. All right, how do you feel about those guys? Good. Now here's the thing, and this is what we did last Thursday. Here I had you choose between alpha, beta, and positron. Here I'm having you choose between fusion fusion, fission, and electron capture. Of course, on the exam, I'm not going to tell you, I'm just going to throw one at you, and it could be any one of the 6, right? So being able to recognize the differences between them, fission versus fusion, for instance, electron capture versus beta emission, like as for instance, alpha emission versus a fission process like this, for instance. That's going to be important. And I might not just give you this thing and say fill in the blank. I might describe it, right? So I could say nickel 59 undergoes electron capture. What would the other product be? And then you would have to say, okay, here's what nickel 59 looks like. You'd say, okay, well, I've got a mass of 59 on the top, and it's nickel. So I'm looking at my periodic table, and I see that nickel is element number 28 right here. And then you're going to say, all right, Mary says it undergoes electron capture. So an electron is 0, -1, E, and that's what electron capture looks like. And then I'm going to make what? And then you're going to put it together. Okay. So I could use my words. You've got to be able to describe it just as well. Okay, just a heads up there. All of the emissions, beta emission, alpha emission, positron emission are these particles that are being emitted. And note, spontaneously, right? Your reactant here is not being hit with anything, right? I'm not hitting it with a neutron to make this happen. I'm not smashing it with another nucleus to make anything happen. So all of my emissions are spontaneous, just one nucleus decomposes and it makes this predictable product plus something else that you can calculate, right? These ones are just a little bit trickier. Sarah's right. If you have what looks like an alpha particle on the reactant side, it's definitely not alpha emission because I'm not emitting that alpha particle. Yes. And the other thing to note is that even if you have an alpha particle on the right-hand side, if this isn't happening spontaneously, if I'm smashing it with a neutron, then it's also not, you wouldn't just call it alpha emission, right? So one kind of difference between, for instance, what's happening here with boron 10 and what's happening up here with, say, curium 245 is that if you have a sample of curium 245, it is a known alpha emitter. You know that it will produce radiation, alpha emission. And so you can kind of take care for that, right? Whereas if you have a sample of boron 10, you're not expecting that sample to decompose on your benchtop and give you potentially harmful ionizing radiation dose, right? Instead, you know it's only going to happen if you shoot it with something, so you wouldn't worry about it like that. Okay. So next thing here, we're talking about rate of radioactive decay. Right? And this is specifically talking about those isotopes which will decay on their own, right? Obviously, not ones that I'm shooting with a neutron to make them fall apart, but things like your alpha, your beta, your positron, even your electron capture is a spontaneous decay event. All of these, you know, how fast do they happen, and can you make them go faster, this kind of thing. We did say at the beginning of this unit, we looked at nuclear reactions and we said, look, because it's in the nucleus and it's totally shielded from what's going on outside, your rate is not dependent on something like a temperature, pressure, or catalyst, right? Doesn't affect this whatsoever. So it's just going to decay when it wants to, whether the atom's in its elemental form or compound, regardless of what's going on outside. Fission and fusion being kind of the only ones where you can kind of force it to do something. different, but that's not a natural decay event, okay? So in terms of rate of radioactive decay, we measure these in half-life. Half-lives, okay? A half-life is the amount of time it takes for half of the sample to decay, right? So after a single half-life, then half of that original amount is available. So you can we can make a chart here and say, look, at time equals 0, this is time, and this is fraction remaining. At time equals 0, you'll have 100% of your sample here, right? And at time equals 1 half-life, I should say time measured in half-lives, then half of your sample will remain, right? So that's going to be 50% right here. One half remains. And then at time equals 2, your second half-life, then half of what you had, it's 1 half-life from here, so half of what you had here remains. So half of half is 1/4. That's the amount that will remain after 2 half-lives, right? And after 3 half-lives, how much is going to remain? Half again as much, right? So that's going to be half of 1/4 is 1/8. And then at 4 half-lives, how much is going to remain? Yeah, 1/16. It is never gone entirely, but there does reach a point at which, for instance, if this is talking about the decay of something that leads to a radioactive, radiation exposure, there's a point at which the radiation exposure that you get from the thing which is decaying meets kind of the background radiation. You can't tell the two apart. So of course at 5, it's going to be half of 1/16, which is 1/32, as you can see. Okay. Now, and you can see this is we call this an exponential decay curve, and it kind of curves and it never really gets to 0, that gets close enough for all intents and purposes. Gotta go through there, and so on and so forth. What I want you to notice here is that this is after 1 half-life. That's 1/2 raised to the 1 is 1/2. At this point, you've had 2 half-lives. That's actually 1/2 raised to the 2, or 1/2 times 1/2 is equal to 1/4, right? And here, at this point, 1/2 cubed raised to the 3rd, that's equal to 1/8, and so on and so forth. Do you guys see that? So the fraction remaining, not the amount remaining, but the fraction remaining from your original amount, and you can say that as we have your amount remaining divided by your original amount. That's the fraction, right? That fraction remaining is equal to 1/2 raised to the number of half-lives that have passed. So if 3 half-lives have passed, then 1/2 cubed means that 1/8 will remain. And if you know the original amount, then 1/8 of your original amount, that's how much remains. Does that make sense? You guys with me? Okay, this is a equation I'm not going to give you on the exam, but want you to kind of understand it conceptually. But if you want to memorize it, it's a great one to memorize, okay? Here is an example problem. Let's see if we can do. We have strontium-90 has a half-life of 28.8 years. If a 5-gram sample is stored, how much strontium-90 will be left after 85 years? All right, so they want to know how much will be left. So we're solving for amount remaining. Just gonna copy this here. Okay, so amount remaining, that's what we want to solve for. That's our X, right? Our original amount, they said it was 5 grams. And we were not given the number of half-lives. Can we calculate that? Yeah, so you're going to say, this is almost an equivalency. 1 half-life is equal to 28.8 years. Right? And so we could do a little dimensional analysis over here and say, look, if I've been around for 85 years and half-life, I'll put that on top, is 28.8 years, then when we do our math, just like Sarah found, 85 divided by 28.8, you get 2.95 half-lives. That's the number of half-lives that have passed, okay? All right. Does that make sense? Everybody follow this math here? So we're gonna put 2.95 in that position. So 1/2 raised to the 2.95 equals X divided by 5. So now we can just solve for X and say, and this is tricky actually, 1/2 raised to the 2.95. I can't use 10 to the X like we've been doing because it's not 10, right? It's 1/2. I'm going to use this X to the Y button, and your calculator might do it different than mine. You might have a caret, and you could do 1/2 caret 2.95. That would be really convenient. It doesn't work here. Here I have to say 1/2 or 0.5. Let's see, 1/2. Okay. 0.5. I'm going to define that as X. And now I'm going to put in 2.95, that's Y, and then hit equal. That's how this calculator wants to do it. 1/2 raised to the 2.95. Try that on your calculator, see how your calculator wants to do it, but you should get a value of 0.1294. Okay, and then when you have, that's 1/2 to the 2.95, multiply that by 5 grams, because this is not the amount that remains, that is just the fraction that remains, right? So that fraction of 5 grams means that after 85 years, we still have 0.647 grams remaining. All right. It's 647 grams remaining. Now, the nice thing about this is you can estimate pretty well, okay? And sometimes that can get you to the answer. So you could say 2.95, that's about 3. That's about 3 half-lives, right? That's pretty close. If I start with 5 grams, I divide by 2, so I'll cut it in half once. Cut it in half twice, cut it in half 3 times, then I should get, after about 3 half-lives, I should have 0.625 grams. This is a little less than 3 half-lives, so I'll have a little more than 0.65 grams. And especially for a multiple choice problem, that's probably going to be enough to get you there. All right. But this is how you would do it here. Let's see here. Let's look at our worksheet and do a couple more problems related to half-lives. Here we go. Let's try this guy. Gold 198 has a half-life of approximately 2.67 days. If a 14.5 nanogram sample of gold 198 is used in the body to treat leukemia, how much is remaining after 8 days? Okay, so this is very much like the one that we just did here, where we're trying to see how much remains after a certain amount of time. Okay. I'm just going to remind ourselves of this for each one of these. Okay. So they give us 14.5 is the original amount, 14.5 nanograms. And we don't know the number of half-lives, but they tell us that one half-life is about 2.67, and they want to know how much after 8 days. So you can say, got 8 days to go, and one half-life is about 2.67 days. You could do a little bit of dimensional analysis here. You can see I calculated this so it was almost exactly as Sarah calculated it, 2.996 half-lives. See what I'm trying to tell you here? It's about equal to 3. About 3 half-lives. Okay, so we could put 2.996 up here, but we could also estimate it pretty closely with 3 half-lives, right? So if we estimate it, then we're gonna say, okay, we start with 14.5 and I'm dividing by 2 3 times, right? Cut it in half, cut it in half, cut it in half again, and that's 3 half-lives, and I get 1.81 nanograms estimated remaining. Versus I can calculate it, and that's totally fine. I'm going to take 1/2 and I'm going to raise that to the 2.996. And as Erica notes, that's at 0.1. This is the fraction that remains. Multiply that by the original amount, 14.5, and it's about to say 1.82 nanograms calculated. Right, so pretty close on both of those. This was calculating how much remaining. This is how long is it going to take for that to decay, and this is a little bit trickier. So here they've given us both the amount remaining, 7.5 grams, and the original amount, 120 grams. And we know how much one half-life is, but now we need to calculate how many half-lives have passed to determine how long the overall time is. Now, to solve for something that's being raised, I'm sorry to do this to you, but to solve for something that's being raised like this, what you have to do is use a property of logs. Just put a new question mark here. Okay. You're going to use a property of logs. You're going to take the log of both sides, log of this side, and the log of that side. And the log of anything with an exponent ends up being, this moves out in front. So the log of 1/2 raised to the number of half-lives is the same as the number of half-lives times the log of 1/2. Oops. It's just a property of logs. So you just take that. And now we can solve for this problem. 7.5 divided by 120. Okay, take the log of that. And now we're going to divide that by 0.5, the log of that. And that gives us the number of half-lives, which is 4. All right, and then we can say, all right, if each half-life is 3.053 minutes, then we can say 4 times 3.053 minutes, and we get something like 12.21 minutes. Is that 4 times 3.053? Yeah, 12.21 minutes. That's how long it's going to take, right? Some of these have very short half-lives. Some of them have very long half-lives. It is typical of radionuclides, that is radioactive nucleuses, that are used in medicine to have fairly short half-lives because we don't want our patients to be radioactive for the rest of their lives. That causes excess damage, not only to them, but also to their loved ones, right? So your procedure might leave you radioactive for a couple days, maybe a couple of weeks, but we don't typically use medicine that's going to be radioactive for longer than that. All right, so here I used the equation, I used that log property. There is another way to do it, right? And that would be to say, how many times do I divide 120 by 2 before I get down to 7.5, right? So I divide it by half, that's 1 half-life. Divide it a half again, that's 2 half-lives. Divide it in half again, that's 3 half-lives. Divide it in half again, that is 4 half-lives. So that was one way to determine that it takes 4 half-lives to decay to 7.5, and then multiply that by 3.053 to give you 12 minutes. If it's not exact, it should still get you pretty close, all right? You can estimate, and it's a good way to double check your work to say, was that about right? Okay. Any questions on that problem? Erica says, so confused. Now, the confusing part is the log thing, right? Yeah. So for the log thing, just remember, this is just a property of logs. And if you don't want to memorize this property of logs, you can just memorize 2 different equations, right? This other one where you say, okay, if I'm, and you'd only use this to solve for the number of half-lives actually. So you could memorize this. The log of the fraction that remains divided by the log of 1/2 that's equal to the number of half-lives. And again, this is the only case where you would be using it anyway, so I may as well just give you, like, this is an equation that you can just memorize if that will help. These are the same equations, just using the properties of logs. And does that feel better than remembering how to solve that problem using the mathematical properties of a log's functions? Okay, yeah, do that then. That'll solve that problem. And then also remember, you can always estimate, right? And that should get you close enough for the multiple choice exam. Let's do this guy. Half-life of iodine, how much was originally present? Oh, okay, so now we're solving for the original amount right here. Because now we have 6.25 grams. And the half-life is 8.1 days, but we've had 24.3 days pass. So 24.3 days have passed, and 1 half-life is 8.1 days. And so Sarah has already calculated that that's like exactly 3. It wasn't even like close, it's exact. Yeah, I'm keeping it easy for you. So 3 half-lives have passed at this point, right? So this is a 3 number of half-lives. So 1/2 raised to the 3rd, 1/2 raised to the 3rd is 0.125. And I'm solving for x. So that means 6.25 divided by x is equal to 0.125. Right? That's how this simplifies. Now to solve for x, I'm going to multiply both sides by x and then divide both sides by 0.125, and that should get me the right answer. So 6.25 divided by 0.125. Solving for x, x was 50, and my units here are grams, so x was 50 grams. Right there. Now again, just to estimate this, you're going to say 6.25 is left after I divided it by half 3 times. I'm just going to multiply it by 2 3 times. So double it once, twice, 3 times. Doubling is the opposite of cutting in half. And then I get 50 grams. Do you guys see that? Okay. These last 2 questions are not talking about half-lives. They're talking about a radiation dose that a patient might get. And patient might get. And I've tossed these out to you because it's just dimensional analysis, and if you're watching your dimensions, then you can solve this problem. And I thought it was interesting to show. One interesting thing is that one measurement of radioactive dosage that you get is the Curie, of course, named after Madame Curie. So here we go. The recommended dosage of iodine-131 for a particular test is 4.2 microcuries per kilogram of body weight. Let's write this here. This is 4.2 microcuries per every 1 kilogram of body weight. That is your dose. Just like how when we had our dosing at the very beginning of the semester and you were doing like grams per kilogram or milligrams per kilogram, it's the same thing. And they want to know how many millicuries should be given to a 55 kilogram patient. And so Sarah's already started this process. She says, look, I know it's a 55 kilogram patient, so I'm just going to stick that right here. They'll cancel out. And that's going to solve for the number of microcuries that were prescribed right here. But make sure that you're paying attention because they're asking how many millicuries should be given. Do you guys remember? Did we do conversions between micros and millis? What do we do there? You might just know there are 1,000 microcuries in a millicurie. They look the same, but the micro, that's the mu, right? Or you might remember, what we did was we memorized that milli equals 10 raised to the negative 3rd, and that micro is equal to 10 raised to the negative 6. So this is kind of the safer one that I would do. And I would say 1 curie is 1 times 10 raised to the negative 6 microcuries. And then further, I could say, okay, yes, but 1 millicurie is 1, wait. Oh boy, I'm backwards. Micro equals this. I've done micro and that together, so I'm totally wrong on that one. Hang on. Go back. All right. 1 curie is equal to 1 Curie. And we said micro is equal to 10 raised to the negative 6. That's how I'm going to remember what goes where, right? I didn't follow my own directions. That's why I had a problem. Okay, and then when millicurie, 1 curie is equal to 1 curie, and milli is equal to times 10 raised to the negative 3rd curies. All right. That should get me there. So we've got 4.2 times 55 times 1 times 10 to the negative 6th. Divide that by 1 times 10 to the negative 3rd, and I get 0.231 millicuries. Of course I did that. Of course I just threw you all the way back into metric prefixes, all the way from the beginning of the chapter. Coming full circle here. Cannot forget your metric prefixes to solve that problem. Does that make sense? All right, and the last one here, we've got a patient who receives technetium 99M for a breast image, 3 milliliter solution, and the activity of the solution is 9.5 millicuries per milliliter. Now this is a solution concentration unit where we're talking about the concentration of radiation that you get. So we have 9.5 millicuries in 1 milliliter. And if they received a 3 milliliter dosage, this one's easy, then 9.5 times 3 equals 28.5 millicuries dose that was received by the patient. That's it. Do you guys have any questions on these problems? Okay. Well, if you guys don't have any questions, I will let you go and see you on Thursday. Erica says, would you give us the unit you want us to give it in? That's a good question, because here I just was like, here it's in millicuries, because I didn't say anything other than what is the dose, right? I didn't tell you the units. Of course, for the exam, the answers all have units, and if they don't, then the unit that's required should definitely be included in the question. Yeah. But I think there was one question we had last time. There was a problem that didn't have units on the answers, but it did say explicitly, like, what is the volume in liters for something like that. So you're welcome. I will see you guys on Thursday for our practice exam. And good luck. Enjoy studying. Stay safe and healthy. Home stretch. We got to make it through finals, right? Nobody's allowed to catch COVID till after finals. Do you feel invincible, Erica? I feel like it might seem like a silly thing to say, but like if you got it and you didn't have long-term effects from it, I feel like, oh, I have a free pass. I can't get it again. I know theoretically it's possible, but you can't eat it. Is that was that because of COVID? Weird. What a weird side effect. But that's COVID for you, isn't it? Is it just that they don't taste good and that they're awful now, or is it does it give you like an allergic reaction? Oh, gross. How long has it been? Sorry, I hope you don't mind me probing your. I think it's really interesting. Oh, that is fascinating. So interesting. It's like you know what that reminds me? That reminds me of like a pregnancy thing, right? People will say like, man, when I was pregnant, like everything smelled terrible and I was so nauseous and I ate this fried chicken once and then I threw it up and like now I can't stand, like years later, fried chicken is gonna make him nauseous. Like there's an association there. And I don't know how much of it is like psychological and how much of it is physiological, but like it's a real thing. That totally reminds me of that. Weird. All right. Well, I hope that gets better, especially if you like eggs. If you don't like eggs, I guess it doesn't matter, but thanks for entertaining my sense of curiosity here. Have a good day.